Okay, so let us start. So I think the recording has started. Okay, so today we're going to go through DC circuits. So this is a chapter where actually the textbook pages are quite few because there's only a few principles introduced here. But the main issues most students have is really about applying those principles. So we're going to look at how we can really look at some of the worked examples to go through the concepts that's highlighted in the chapter. Okay, so let's start. So first thing in DC circuits, they start with 16.1, which is a series circuit. Most of you should be quite familiar with what series circuit is. Okay, so let's start the learning outcome. So we state that for series circuit, the current at every point is the same. That's one thing that we're going to cover later. We're also going to learn that the sum of the potential difference across each component, so the PD across each component, if you add them all up, this is equal to the PD across the whole circuit. Okay, so every single component, you add all the voltage. PD represents voltage. Okay, so you add all the voltage up across for each component equals to the PD across the whole circuit. So we're going to cover that. Next, we're going to learn how to calculate the effective resistance of the resistors in series. And last one, we're going to apply the principles. So you can see here, the first part covers I, second part covers V, the third part covers R. Okay, then we're going to use this 3 here to go and learn how to apply to solve problems. So let's start. Okay, first thing, what exactly is a series circuit? Okay, in a series circuit, the components are connected one after another in a single loop. So the battery connected to one light bulb, connected to another light bulb, connected back to battery. This is a single loop. Single loop. Okay, so if you have a single loop, this is considered series. And when you talk really more in terms of the circuitry, in terms of the stuff, right? In terms of circuitry, right? Really what it means is that series circuit has only one path through which the electric charge can flow. Okay? So it is only one path which the electric charge can flow. So let's go in depth now. Once we know what series is, we're going to go into the current part of it. Okay, how does a current work in a series circuit? So we're gonna, in figures table 16.1, it actually shows two circuits which the resistors are arranged in series. This one, single resistor. This one, I have two resistors in series. Okay, so let's look at the single resistors one. This is an ammeter. Okay, in case you are not so sure. So ammeter actually measures the amount of current flowing at that particular point. Okay, so I got two ammeter here. So A1 will measure I1. A2 will measure I2. So I say ammeter 1 will measure the current I1. A2, ammeter 2 will actually measure the current I2. Okay, so when they did this, okay, when they have this circuit, they actually put the two ammeter here, they realize that the current I1 is actually equals to the current I2. So the conclusion or the principle or the concept that you can apply from this is that the same current flows into and out of resistor R. So the current that flows into R, which is I1, and the current that flows out of it, I2, they are the same. Okay? So in a series circuit, the current flowing into the resistor and the current flowing out of the resistor is the same. So that's what the first example is talking about. In the second one, okay, we're now connecting resistor R1 and R2 in series. Can you see they are just side by side? There's still only one path which the current can flow, and hence this is still a series circuit. A1, ammeter 1 measures the current I1. Okay, this prime here is just to tell you that it's different from this current. So I1 prime. A2, ammeter 2 measures current 2 here. A3, ammeter 3 measures current 3 over here. Okay, that's flowing through the circuit. Now, what they realize is that when they put the 3 ammeters here, and they switch the circuit on, okay, they realize that, oh, all the ammeters show the same reading. They realize that I1 equals to I2 equals to I3. All the 3 readings are the same. So we know that the same current flows through R1, same current flows through R2. So going in, going out, going in, going out, the current throughout the whole circuit is the same. Therefore, the conclusion based on this two is that in a series circuit, the current at every point is the same. So need not be these 3 points. If I put an ammeter here, A4, to measure I4. I put an ammeter here, A5, to measure the current flowing out I5. What will be all this reading? You'll know that I1, I2, I3, I4, I5 all will be the same. I can also add a few more resistors here, and it will still give me the same thing. The current throughout the whole circuit, okay, is the same for a series circuit. So this is the first thing. These are the examples, okay, to highlight some of the results. And then from there, the conclusion we can draw is that the current at every point in a series circuit is the same. Okay, so that's for current. Now, we're going to go into potential difference now. So potential difference, we know that it's measured in volts. Okay, the SI unit is volts. So table 16.2 shows an electric current in which the resistors are arranged in series. Okay, so I got two resistors in series. This set out to measure a potential difference across each resistor and that across all the resistors in the circuit. So what we have here is a R1 and R2 connected in series. So I want you to focus on this red color line here. Okay, this orange or red color line that I'm drawing. This is the circuit without any voltmeter connected to it. So I want you to focus on this. Because I think with the voltmeter drawn in, it looks very complicated. What I want to show you is this circuit that we draw here is exactly the same as the circuit that we have drawn here. Okay, just that instead of putting ammeters, now I put voltmeters. Okay, can? So that's the first thing. Okay, so identify that these two are the same diagram. Okay, it's just R1 and R2 connected in series. Now, what they did here is this. Okay, to measure the potential difference of R1, so they connected a voltmeter parallel to R1. So connected to the start before R1, connected to after R1. This will help me measure the potential difference of R1. Okay, so the potential difference of R1, we'll actually label it as V1. So V1 actually measures the potential difference across R1. V2 measures the potential difference across R2. What is this VE over here? Okay, this VE actually serves two functions. Okay, first thing, by connecting the voltmeter like this, is actually the same as connecting the voltmeter. I use green color here. Connecting the voltmeter like this. VE. So first function that VE does is it actually measures the potential difference across both R1 and R2. That's what VE actually represents. This is one of the things it can represent. Next, VE can also represent that it's actually measuring the potential difference across the electrical source. And we also know that the potential difference across the electrical source is also the same as saying I am finding out what is the EMF, which is the electromotive force. If you're not sure what electromotive force is, okay, you can go back to the previous lecture that we've done on the current of electricity. Okay, so VE actually has two parts to it. One is measure potential difference across R1 and R2, that's what it can represent. The other thing VE can represent also is to measure the potential difference across the electrical source, which is also the same as measuring what is the EMF. Okay, so first things first, let's look at this. So what they realize is that V1, so when they switch on the circuit, they look at the reading of V1. They realize that V1 plus V2 will give me the same reading as VE. So what we realize that when we have two resistors connected in series, the sum of their potential difference is equals to the potential difference across the whole circuit here. Okay, so the potential difference V across the whole circuit is equivalent to the sum of V1 and V2. So VE equals to V1 plus V2. What's the second thing they also realized is that if this was a 5-volt battery, okay, 5-volt battery, VE will also show 5 volts. Okay, what it means is that actually by having VE over here, you are also measuring the EMF of the electrical source, the electromotive force. Okay, so based on this, what conclusion can you draw? What you realize that, oh, sure, the VE is equals to V1 plus V2. Okay, but if I got more resistors all connected in series, I can add all their potential difference up and I can get the VE, which is the EMF, or the potential difference across the whole circuit. And hence, the conclusion based on this thing here is that in a series circuit, the sum of the PD across each component, so sum of the PD for R1 plus the sum of the PD of R2 plus the sum across R3 and blah, 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 is equals to the PD potential difference across the whole circuit, which this one here is actually equals to the EMF. Okay, Ken? So this is what you can conclude based on potential difference across a series circuit. So we have done the current part. We know that current is the same throughout the circuit. Okay, for a series circuit. For potential difference, we realize that is the sum of the potential difference across each component is equals to the potential difference across the whole circuit. Okay, so that's for current, that's for potential difference. Now, in terms of resistance in a series circuit, I think this one most of you are already very familiar with it. This one, all these points that I'm writing here is just to explain, okay, explain more in depth. You don't really need to go so in depth into all this. Okay. Key idea here, to find the total resistance, you just take the resistance and add it up. Okay. So what it means that you can see here R1 and R2. To find the resistance in the series circuit, what I do is R1 and R2, if they're connected in series, I can just combine their resistance. Okay, that will give me the total resistance. So the total resistance of the multiple resistors in the circuit, so there are two resistors in the circuit, the total resistance, you just add them up, R1 plus R2. If I got 3 resistors, I'll plus R3. If I got 4 resistors, I'll plus R4. Blah, 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 so on and so forth. Okay? So in conclusion, what we know is that in a series circuit, the effective resistance R is the sum of all the resistance. Right? So far, series circuit, I think is not too difficult. I think we are getting it there already. So because what we have touched is on the current, the voltage, and the resistance, let us now try work example 16.1. So 16.1 shows 3 resistors value 2, 4, and 6 connected in series to a 6 volt dry cell. Okay, what is the effective resistance of the 3 resistors? So 1, 2, 3. What's the effective resistance? Because these 3 resistors are connected in series, so we know that to find the effective resistance, we add up all the resistance. So 2, 4, and 6, add them up, you got 12 ohm. So quite a simple first question for a good start. Next, what's the current measured by 1 and by 2? One is ammeter 1, one is ammeter 2. So what we know is that the current and I1, we know A1, okay, will help us find what is I1. So ammeter 1 will measure current 1. Ammeter 2 will actually measure current 2. Alright, there's no I1 and I2 over here. Okay, but I'm just writing this out so that to know that A is the instrument. The thing that you're actually measuring is the current. The symbol should be I. Okay? Now, so what we know is that the current will all be the same. And hence, since we know that the total voltage, so V total, we know is 6 volts, which is the EMF. We know that the R total, okay, or effective resistance is actually equals to 12 ohm. Now, so what we can also find out is what's the total current that's flowing out. So you realize I purposely write the word total here so that is to let you know that whenever you're using V equals to IR, all these subscript words here must be the same. So I want to find the current flowing out, which is I total. I need to use V total, I need to use R total. So V total is equals to I total times R total. What exactly is this formula? It's just V equals to IR. That's what we are finding here. Okay, so you rearrange, you got I equals to V over R, which then you sub 6 and 12, you're going to get 0.5 ampere. So we know that A1, okay, we can know that the I total is actually equals to 0.5 ampere. And since I know I total, because the current flowing through in a series circuit is the same throughout, I'll know that I total equals to I1. I total will also be equals to I2. So therefore, I'll know the current measured by ammeter 1 will be 0.5. which is the same as your I total. The current flowing through A2 will also be 0.5, which is also the same as your I total. Okay, Ken? So this is for this B part 1. Part 2, okay, is really to measure the current. Applying the idea of current in a series circuit is the same throughout. Okay, next, let's calculate a potential difference across each resistors. We know that each resistors, the potential difference will be different. Why? Remember, because we know that in a series circuit, the sum of the PD across all the components will be equal to the PD across the whole circuit. So we know that the PD across 2 plus the PD across 4 plus the PD across 6 must add up to 6. So we know that they will confirm be different since different resistors, right? But what we realize is that to find, okay, V1, okay, so V1 is actually, think of it as you put a voltmeter 1 over here. V2 is like this. V3 is like this. Okay, V3. So to find V1, to find V1, I need to take I1 times R1. So V1, which is this one here, is I1. I1 I know is the same as I total, therefore you realize they didn't write the 1 over there. So it's just the total current times R1. Okay, so 0.5 times 2, 1 volt. Voltmeter across the 4 ohm will just be I2 times R2. What's the current flowing through the 4 ohm? Is the same as the total current, which is 0.5 also, multiplied by the resistor 2, which is 4 ohm, you get 2 volts. Then you apply the same thing for the third one, 0.5 multiplied by 6, you got 3 volts. What you realize that this thing should add up to 6 volts, because the sum of each of the potential difference, when you add them all up, it should give you the EMF. Okay, so take note of this. And in a series circuit, one more thing to note is that the PD across a resistor of a larger resistance, okay, is greater than the PD across the resistor of a smaller resistor. What do you mean? Can you see 6 ohm, 3 volts. 4 ohm, 2 volts. 2 ohm, 1 volt. So if in a series circuit, the current only flowing one direction, right? Okay, that doesn't split or anything. Well, you realize that if there's more resistance, the voltage or the potential difference will be higher. Smaller resistance, the potential difference will be lower. That's what part 2 is saying. Okay, so this is quite a simple question. If this was in your O-level paper or combined science prelim paper, this will be worth about 1 mark. This one most probably worth 2 marks. This one here, if they really ask you find all 3, it could be worth to 3 to 4 marks. Okay, so if really this comes out, it's quite a good amount of marks, about 7, aga, okay, 6 to 7. So quite good marks and not too difficult to do. Okay, so if it comes out, please make sure you get it correct. Next, we're gonna go on to parallel circuit. Okay, so we're done with series, we're gonna go on to parallel. So parallel circuits, what we're gonna cover here is that for parallel circuit, the current from the source is equal to the sum of current in each branch. Okay, we're gonna cover that, so this for I. The PD across the separate branches is the same, so we're going to learn that the PD across the separate branches is the same. A little bit different from the series side. We're going to learn how to calculate the effective resistance of resistors in parallel. And last one, we're going to learn how to apply. And this part here, the apply part, is definitely the important part. Because you can know all the principles, but you know how to apply, all the DC circuits will look very off to you and you find it quite difficult. Okay? Next. So what exactly is a parallel circuit? The components, okay, are connected to the EMF source in 2 or more loops. So if you look at this diagram carefully, okay, let's use red color here. The current is flowing in this way. Once it reaches this point, okay, the current can flow either the pink side or it can flow to the yellow side. So you can see there's 2 paths, okay, 2 paths that the current will flow. But the interesting thing is, the 2 paths after splitting, they will still come back to the same path. Right? They'll still come back to the same path. So there is a split. So this is considered parallel circuit here. Okay, but take note, after the parallel circuit is connected, it will still always come back to the same wire. Okay, so when there's a split, there will always be a connection back. So what exactly, in terms of a definition for parallel circuit, it is a circuit that has more than one path through which electric charges can flow. So go through like that and go either the pink path or the yellow path. Okay, more than one path. So how is the current in a parallel circuit found out? Or how do you find the current in a parallel circuit? So let's look at 16.3. 16.3 shows an electric current in which resistors are arranged in parallel. So you got R1 and R2. Ammeters are added to measure the current at different points in the circuit. So they add A over here, one ammeter here. This ammeter actually measures the total current flowing through the whole circuit. A1 measures I1, A2 measures I2. So when they switch the circuit on, what they realize that A, which measures I, is actually equals to I1 plus I2. So this was based on, if you just have the circuit connected, you switch it on, you'll find out that this is what is happening. So conclusion is, we know that current flowing from the cell splits at junction X. So at this point, current will split to A1 and A2. Sorry, I1 and I2. Okay, and they will recombine back at junction Y. So based on this, what they realize is that for n branches in a parallel, so if there are two branches, okay, the total current will just be equal to current in branch 1 plus the current in branch 2. If I got more than that, it will be I3, or if I got 4 branch, it will be I4 plus whatever, until depending on how many branches you have. Okay, so in conclusion, based on that, in a parallel circuit, the sum of individual current each parallel branch, if I add each of the branch up, the current in them, this equals to the main current flowing into or out of the parallel branch. So into and out of, right? The main current flowing into, the main current flowing out of is actually the sum of all the currents inside the parallel branch. Okay? So this idea of how it actually works out, it gives you an idea of, okay, it's not like they purposely had a principle there, it's just that when they did the experiment, they realized that was what they found out, and hence this principle of this concept could be applied to your theory. Okay? Next one, potential difference across a parallel circuit. So 16.4 shows an electric circuit in which the resistors are arranged in parallel, so R1, R2. They are set out to measure the potential difference across the resistor and across all the resistors in the component. So I want to first draw this out first. Right? This is actually the main path that the current will flow. This red color path. Okay? This is to make you be very clear in terms of how the circuit, the main circuit actually is. Okay, once you're clear on the main circuit, then you can focus on the voltmeter already. So what exactly does V2 measure? V2 actually measures the voltage or the potential difference across R2. V1 measures the potential difference across R1. What exactly is VE? As mentioned, VE has two parts to it. One, it measures the potential difference across R1 and R2. Okay, sorry, I draw too many lines here. Okay. The other thing is that VE also measures the potential difference across the electrical source. So what they realize is this, is that when they switch the circuit on, the value of V1 is equal to the value of V2. And the value of V1 is equal to VE. The value of V2 is also equal to VE. And therefore, what we realize is that the potential difference across R1 is equal to the potential difference across the R2 is equal to the potential difference across the electrical source. So the potential difference VE across the whole circuit is equal to the PD across each resistor R1 and R2. Okay, that's what we got here. And of course, the next one we do which is the same as previous one, VE is actually equals to the EMF of the electrical source. So what can we conclude here is that in parallel circuit, the PD across parallel branches is the same. So this branch and this branch, the potential difference will be the same. Okay? So that's for the potential difference in a parallel circuit. Now, how about resistance in a parallel circuit? Okay? So resistance in a parallel circuit is a bit more complicated compared to resistance in series circuit. So what you realize is that to find the effective resistance of two resistors in parallel, you need to apply this formula. R equals to 1 over R. R is the effective resistance or the total resistance. Okay? This is actually equals to 1 over R1 plus 1 over R2. I got a third one, it's 1 over R3. So therefore, you can simplify into this formula over here. Now, for my classes, I actually highlighted that actually this formula, when you key in, people tend to make a very common mistake. They forgot to re-invert the whole thing. As such, I say, okay, maybe don't memorize this. Remember the formula as R equals to, same thing, is 1 over R1 plus 1 over R2 plus dot, 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 1 over Rn. Now, what you realize that I got this bracket here. What's the bracket here for? In your calculator, when you want to calculate the effective resistance, you do this, have the bracket there, with a power of -1. This will mean that it is to flip the whole thing around, okay, to find the reciprocal. So this is the formula you're going to use to measure the resistance, right? To be more precise, the effective resistance of the resistors connected in parallel circuit, in a parallel circuit. Okay, so this one I think most of you are also quite familiar with it already. So let's look at worked example 16.2. Right, 16.2. So 6 volt battery once again connected to 1 ohm, 3 ohm, 6 ohm. Now, this 3 ammeter, I want to put this very clearly. A3, A2, A1 actually measures different things, although they look the same. A2, if you put it here, is actually equivalent to measuring the current flowing through the 3 ohm. It's like just beside here. A1 is actually, imagine it's like placed here. A3 is actually measuring the current, okay, the main. A3 is measuring the main. A2 is actually to measure the 3 ohm, the current through the 3 ohm. A1 is actually to measure the current through the 6 ohm. So what you realize is that there is no ammeter to measure the current through the 1 ohm. So if I want, I should actually attach a A4 over here to measure the current across through the 1 ohm. Right? A3 actually measures the main, because you can see A1, A2, A4. These are 3 separate branches. Right? The current through 1, the current through 3, the current through 6 is represented in A4, A2, A1. If you add these 3 up, you should get A3. Okay? So first things first, let's look at the question in terms of answering them. Part A. What is the effective resistance of the 3 resistors? Okay, so you're going to apply this. So you're going to take the effective resistance is equivalent to the 1 over the 1 ohm, 1 over the 3 ohm, 1 over the 6 ohm. Okay, 1 over R will be equivalent to 9 over 6 if you press your calculator. Eventually, you must invert it. So R equals to 0.667 ohm. If you follow my formula, it will actually be R equals to bracket 1 over 1 plus 1 over 3 plus 1 over 6 to the power of -1. You press your calculator, when you do this, you get still 0.667 ohm. It's the same thing. Right? Just that I added the power -1 here. It's actually taught by one of my students. One of my students actually teach me this. Okay, so instead of memorizing formula like this, they actually converted it to like this. Okay, simpler for those who are not so familiar or not so good with math. Okay, next one, part B. What is the potential difference across each resistor? This is kind of lame because what you realize is that when you have resistors connected in parallel, all of their potential difference are the same. And each of these potential difference will actually be equivalent to the EMF of the cell. As such, on part B, the answer is the PD will be 6 volts, 6 volts, 6 volts across each of the resistor. Right, each of the resistor. Now, C. What's the current measured by ammeter A1, A2, and A3? So A1 is actually the current across the 6 ohm. So what I know is that the current across the 6 ohm is what I want to find. I need to use the voltage across the 6 ohm. I need to use the resistance across the 6 ohm. I need the resistance of 6 ohm. So obviously, resistance of 6 ohm is 6 ohm. We recognize that the potential difference across each of these resistors is the same as the EMF, which is 6 volts. So take 6 divided by 6, you get 1 ampere. Okay? Tada, 1 ampere. Now, how about for the 3 ohm? What you realize is that, once again, to find the current across the 3 ohm is actually to find A2, which you will be able to find. Let me rephrase this. Actually, to find A2, actually, you are trying to find the current across the 3 ohm. which then you take the voltage across the 3 ohm divided by the resistance of the 3 ohm. So the voltage, the potential difference, you realize we mentioned is already 6. The obviously resistance of the 3 ohm resistor is 3 ohm. So you take this divided by this, you're going to get 2 ampere. Okay, so that's the value of that's the value of the current through here. Sorry, my mistake. This is actually not A2. My bad. Okay. So A2 actually is the sum of 2 branches. It's actually a current through here plus the current here add up. My bad. So A2 actually needs to add up the current across here and across here. Okay. So what is going to happen is that for A2, it actually measures the 1 ampere here plus the 2 ampere here. Because we measured is 2 ampere here. Therefore, A2's reading is actually 3 ampere. So my bad, A2 is actually not to measure the current across 3 ohm. It's actually to measure the current of these 2 branches add up. Another trick here. I say, okay, but then after that, the last one is to measure the main one. So I need to measure, I know A2 is 3 ampere now. A3 here actually will be 3 ampere plus the current across here. So I need to find the current across the 1 ohm. So how to find the current across the 1 ohm? I know the potential difference here is 6 volts. I know the resistance across here is 1 ohm. So therefore, I know I of the 1 ohm is actually 6 ampere. This guy here is 6 ampere. So A3 will then be equivalent to this branch plus this branch over here. So 3 plus 6, therefore the answer is 9 ampere. 9 ampere. Okay, so this is to measure the value of A3. So realize, first find this one over here. Find the current that's coming from the 6 ohm. A2 will just be equivalent to the current flowing through a 3 ohm plus the current flowing through a 6 ohm. Because can you see these 2 branches are going to combine to give you A2. Next, to find A3, you take the current flowing through A2 plus the current flowing out of of the 1 ohm. These 2 combine, you get A3. So that's how you do part 1, part 2, part 3. Now, for part 3, there is a different idea also. Okay, the other way of doing it is that you know the voltage is 6 volts. You know that A3 actually measures the I total. The A3 actually measures I total. So to find the I total, what I can do is I take V total. I know that is equals to I total times R total. So R total you actually measured here is 0.667. V total is 6. So 6 equals to I total. This is actually the A3R. Multiplied by 0.667. So you do your math. I total is actually equivalent to 6 over 0.667. And if you do properly your I of the total, let me screw this up. This will actually give you the same value of 9 ampere. So take note, this is an alternate way of measuring it. But part 1, part 2, part 3, if you get the key idea, I think that will be sufficiently good. Okay. But as I mentioned, as I'm going to mention now, so to take note of this, current of like DC circuits, right? There's not only just one way of doing it. There are quite a few ways you can go about approaching the question. So don't only think of it as there should be only one way of doing it. It can be multiple approaches to try to get to the final answer. Okay, so that's for this one over here. Now, I think this part over here, they are explaining a little bit more. So I want you to just think, well, this one, people tend to miss it out, but I thought it's really quite a good additional info. Now, when additional resistors are added in parallel to a circuit, okay, when I add more and more resistors in parallel, do take note, the effective resistance decreases. So when additional resistors added in parallel, actually it causes the overall resistance to drop. So more resistors added in parallel, the overall resistance actually drops. Okay. Next thing, in a parallel circuit, the PD remains the same across each branch. This is what we already have picked up from the previous part. Okay. So when R2 is connected to R1 in parallel, we know that the current will increase. Therefore, the effective resistance actually decrease. This is an explanation of this part over here. Okay. So this is the key point. This part here is an explanation of this. Okay, so explanation to emphasize on this because the PD is the same. When I add more and more resistance, more and more resistors, actually I'm adding, there'll be more and more current flowing. So I1, I2, if I add one more, there'll be I3. So there'll be more and more current flowing through the whole circuit. And since we know overall resistance is equals to the V total divided by I total, since I keeps increasing as I add more and more resistors, but V stays the same, so constant divided by a bigger and bigger number, R will actually decrease along the way. So just take note of that, okay, because this tends to be asked at the last few parts of the electricity question about those explanation type. So if you want to score your A's, definitely this is something that you need to take note of. Okay, and okay, this water flow model actually just to help you to understand the whole circuit a little bit better in terms of parallel circuit. Okay, now the flow of water they mentioned is represents current, so water flowing, where water flowing. So there's a flow of water here, there's a flow of water here, flow of water here, and then the pump to pull it back. The water level in the bathtub represents potential difference. Do take note, they mentioned constant water level. Okay, so the potential difference stays constant, right? Quite interesting, The pump represents the electrical source. So this is like the electrical source. Now, when hole 1 is unplugged, it means when current is flowing through here, the water flows out slowly. The pump is turned on to maintain a constant level of water in the bathtub. So if down here is draining 1 liter per second, the pump here will actually put in 1 liter per second. Okay, this is when there's only a series circuit. So the current flowing through 1 liter per second, 1 liter per second. Now when I unplug hole 1 and hole 2, okay, the water flows out from the bathtub. So imagine down here 1 liter per second. Down here, imagine it's a bigger hole, 2 liter per second. Okay, water will flow out faster. And can you see water is flowing out 3 liter per second? So in this case here, the pump used to work at 1 liter per second. Now the pump needs to work harder. It needs to pump out how much water? 3 liter per second to compensate the water flowing out of these 2 holes. And therefore, this is the similar concept in the sense that because the pump will want to ensure that this is a constant water level, when more holes are pumped in, when there are more holes or when there are more paths for the current to flow, the pump will need to work harder, okay, to ensure that the water level stays constant and the potential difference stays the same. Okay, so this is quite an interesting concept using the water pump method. Really, the constant water level is actually just to tell you that it's trying to maintain the potential difference. Okay, so this is to highlight the idea of current. When there are more branches, you realize the total current will actually increase. Okay, but the potential difference across each of them actually stays the same. Okay, now connecting light bulbs in series or parallel. What are the advantages? What are the disadvantages? So first things first, when you're connecting light bulbs in a series or parallel, I want you to look at this. The light bulbs are identical. Identical light bulbs means that the resistance are the same. This is a prerequisite for this. Otherwise, it's going to be difficult to try to explain it. Okay, so in a series circuit, what you're going to have is, if you have 2 light bulbs in series, each bulb will receive half of the voltage. Because 2 bulbs, half the voltage. If you have 3 bulbs, it will be 1/3 of the voltage. Okay? Each bulb, the resistance is R. So therefore, the current will be V over 2 divided by R. So it's half of the overall, half of VE over R. Okay, a bit chima, but let's put this as for now. If I got same circuit except that instead of the 2 light bulbs connected in series, now I connect them in parallel. Because in parallel, what you know is that the voltage across each bulb will be the same as the voltage of the electrical source. So each bulb will have VE as the voltage. Each bulb, once again, resistance is still R. What you realize is that the current flowing through each bulb will be VE over R. I want you to compare this. What you realize is that the current flowing through this bulb and this bulb, okay, let's call it I series, okay, compared to this one here, IP, which stands for I parallel. What you realize when you compare I series and I parallel is that I series, okay, is lesser than I parallel. Okay, so if there's lesser current flowing through a light bulb, obviously you know that the light bulb here will be less bright, dimmer. The light bulb here will definitely be brighter. Okay, so that's comparing the series and parallel. And if I connect more and more light bulb in series, you realize that the light bulb will actually get dimmer and dimmer and dimmer because the voltage is now split across, the potential difference is now split across more and more light bulbs. But if I connect them in series, you realize that the light bulbs, the potential difference stays the same. As such, all of them will still light up in equal brightness. I can add more and more and more, but the brightness of each bulb will not change. Okay? So what's the advantages of using parallel circuits for lighting? So what we know is that when bulbs are connected in parallel, they will glow more brightly when connected in series. So bulbs connected in parallel will definitely glow more brightly when connected than when connected in series. Okay. Second thing is that when in parallel circuit, the good thing is because they are all connected in parallel, when one of the bulb blows, and when all the bulb is malfunctioning or the circuit has problems, the other bulbs will still work. So there are two advantages of using parallel circuit. But in terms of disadvantage, you do see that, yeah, the current is actually quite higher. Okay. If I got more and more light bulbs connected in series, it will draw more and more current. If it draws more current, it means that the source, okay, of the circuit will need to provide a larger power, which means that it will also be depleted more quickly than in a series circuit. So your battery will actually, or your electrical source will be drained out faster if you connect it in parallel. Okay, which makes sense, right? I mean, if all the light bulbs are so bright, obviously you will drain more energy from your battery, right? Or your electrical source. Right? Quite common sense. So two advantages for you to take note, one disadvantage for you to take note. Okay? Now, so the key ideas what you have here is that comparing series and parallel, series circuit, the current is the same throughout the circuit, but in parallel, okay, the sum of the current in each branch will add up to the total current, or the current in the main branch. Okay, next, potential difference in a series circuit, the potential difference across each component, V1, V2, V3, blah, 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 is equals to the voltage of the electrical source. Whereas for parallel circuit, the voltage across each branch is the same, okay, for all of them, which also could be the same as the electrical source. Okay, last one, resistance. Series circuit, you just add all the resistance up, very simple to calculate. For parallel circuit, it's actually a little bit more complex. You need to take 1 over the resistance plus 1 over resistance, blah, 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 blah. As mentioned, the one that I normally teach my student is this. Okay, it's actually just a manipulation of formula, which I learned from another student. Okay, so, yep, this is what we have covered so far. I think really you can go and try test yourself, okay, but I thought there's one more part here which really highlights the main issues that most of you will encounter when you're doing DC circuit. Because resistors are not so easy, always connected in series, always connected in parallel. It's always a mix. Therefore, I want us to look at work example 16.3. It gives a very nice idea of what are the examples you will typically work with. Okay, so I got figure 16.1, I got figure 16.2. Okay, so the effective resistance of each of this, how to go about calculating them. Okay, first one, so 3 ohm, 6 ohm, 4 ohm. These two are connected in parallel, this one connected in series to these two. So what you can do is combine these two in parallel first. Okay, because 4 you can't add to this, but because these two are in parallel, you can just add them up together. So what you're going to do, you're going to apply the formula. R1 equals to 1 over 3 plus 1 over 6. You got 3 over 6 ohm. You invert the whole thing. R equals to 2 ohm. So this diagram 16.1 can actually be considered as like this. These two resistance add up is actually equal to 2 ohm. So this complex diagram actually now looks like this. And when I have two resistors like this connected side by side, what's the total resistance? Take 2 plus 4, you get 6 ohm. Quite a simple one. So key idea, work with two resistors at a time, okay, that you know you can combine together. So that's for this. Figure 16.12, this one here, instead of parallel to a series, this is like a series within a parallel circuit. So what I can do is, since these two are connected in series, why not just add them up first? So I can take 3 plus 4, I'll get 7. And hence this diagram can be simplified into something like this. Now I got two resistors connected in parallel. Easy. 1 over the total resistance equals to 1 over 7 plus 1 over 6. You get 13 over 42. And hence RT, or the total resistance, will just be 42 over 13. And when you press your calculator, you're going to get 3.2. So this kind of questions, you must be able to calculate, because this will typically be about the first question or second question in a DC circuit kind of question for you to attempt. Now 16.4 obviously is the more typical one that you will see in your exam paper. This one just purely resistors only. The one that you normally see has the voltmeter, has the current flowing through, and that's where the main problem comes. So let's see this carefully. The cells in 16.15 has an EMF of 6 volts. 6 volts, Calculate the effective resistance of the two resistors connected in parallel. Oh, they only want the two resistors connected in parallel first. So I want these two. What's the total resistance? So 1 over R equals 1 over 6 plus 1 over 12. Find the resistance. It's just, you see, they are using the formula that I showed you. 1 over 6 plus 1 over 12, invert it, it equals to 4 ohm. Therefore, this diagram now could be simplified into this. Can you see? Because this effective resistance is 4 ohm, you can simplify into this. Now they ask, what's the current I1 from the cell? So I1 from the cell is here. So I1 from the cell is actually I total. I total. So if I want to find I total, I need V total, which is this. I need R total, which is this. So in actual fact, I know R total is just 14. I know V total, which is 6. So to find I total, you just take V total divided by R total, 6 over 14, 0.43. So I know the current flowing through here, 0.43 ampere. Now, next they ask, what's the potential difference across XY? And what's the potential difference across YZ? So across XY is over here, measure a voltmeter here. So I want to find this, let's call it VXY. Now to measure VXY is actually the potential difference across the 10 ohm. Okay, measure the potential difference across 10 ohm, which is the same as measuring the potential difference across here. Okay, so you realize having a simplified diagram actually helps you quite a fair bit. So if you can redraw and simplify the diagram, that will definitely help a lot in your DC circuit. So to find VXY, which is the voltage across the 10 ohm, so VXY is actually V of the 10 ohm. I got R of the 10 ohm. You can see R resistance of 10 ohm is 10 ohm. The current flowing through this, we already calculated, is 0.43. Therefore, if R1 is the 10 ohm resistor, I1 is 0.43. To find the potential difference, you just take I1 times R1. You're going to get 4.3 volts. Okay? Now, across YZ, because we know this is also 0.43, so what you could actually do is take 0.43 multiplied by 4, you can get the answer. However, there's also a simpler way of doing it, which is we know that the potential difference across XY, potential difference across YZ, if you add them up, the potential difference across the components will actually be equivalent to the EMF, the cell. So I know since, so this, before you go into this, which means that you will know if I substitute the values in, 6 volts, 6 is actually equivalent to 4.3 plus V of YZ. So if you rearrange, you're going to get this, and hence the final reading is actually 1.7 volts. Okay, you can also, to find this 1.7, you could have also taken 0.43 multiply by 4, and you're going to get 1.7 also. You'll get 1.72 to be exact. Okay, next, find the current I2 and I3. If I know the potential difference across here, which already found is 1.7, so I know that the potential difference here, I put a voltmeter here, is 1.7 volts. Potential difference here is 1.7 volts. So if I got a potential difference, I got a resistance, I can find current. So I2 is actually taking the voltage across the 6 ohm divided by the resistance across the 6 ohm. So you get 1.7 divided by 6, 2.8, 0.28 ampere flowing through here. I3 is taking the potential difference across the 12 ohm, which is 1.7, divided by the resistance of the 12 ohm, 12, you're going to get 0.14. Okay, so the key idea here when you're doing such a question is to break it down step by step, yet still being aware of what's happening throughout the whole circuit. Okay, so I say again, the key to doing this is to break down the thing step by step, but still keeping in mind what's happening throughout the whole circuit. It is not easy, definitely, it takes practice. So whenever you are doing DC circuits, the key idea here, break it down step by step. Don't look at everything one shot, then you try to do compound carbide. So main idea, do it step by step, and you will get a better sense of what's happening. Okay, so to find out all this, generally you definitely need to apply V equals to IR. You need to apply resistors in series, resistors in parallel, and you need to apply the principles that we'll talk about over here. Okay, so that will be how you're going to go about doing DC circuits. It's really, as I'm going to say again, step by step. Okay, one thing at a time. Apply the principles one thing at a time. Okay, so that will be it.